Okay, so let's do products as a prototype. And their universal property. Okay, so now let's just work in a general category. Okay, so let's work with a category C. C is going to be a category. Right, and then we'll take objects, I don't know, A and B will be objects of the category C. Okay, and so if the product A cross B exists, then it satisfies a universal property. Okay, what is the universal property? So the universal property is as follows. Okay? And this is kind of going to be typical. So it says the following. If C is an object in the category, right, and C maps to A, so it has a morphism here. So if we have a map here, and we have a map here, so this is a morphism in the category to B, right, then it factors through A cross B. Okay, so A cross B comes with two maps. This is the projection onto A. This is the projection onto B. Right? And it says that this thing exists. Right? And it's unique. There exists a unique map phi, and this thing depends on F and G. Okay, so what it says is that if you have an F and you have a G, then I can make a map to this thing such that these two things commute. So, okay, so what this says is that for all pairs of maps, F from A to B, or from C to B, and all maps G from C to A, there exists a unique map phi from C to A cross B, right, such that, and I'll move this up a little bit, such that this diagram commutes, meaning that if I go here, then here, then I get this. And if I go here, then here, then I get this. Such that, so phi, so F is equal to the projection of A followed by phi, and G is equal to the projection to B followed with this thing. Okay, and so let me just say another thing about this. Okay, so it says that these two things exist, and it's unique. So this map is universal. So these projections here are universal among things with maps to A and B. Okay, so so let me just say a quick note here. Is that in any category in the world, this whatever we call A cross B, right, when it exists, always comes with maps which are the projection to A and the projection to B. Okay, so the data of a product is not just this object, but it's an object with these two maps, And it has the universal property that if there's a map to A and there's a map to B, then there must exist a map to A cross B such that F is really this composition and G is really this composition. That is the universal property of products. Okay? So, all right. So now I'm going to kind of recast this in a different way. So I'm going to stop here, and now I'm going to kind of recast this in a different way. All right. So let's recast this thing about products. So what do I want to say about products? Okay, so let me just give you the official definition of initial and terminal objects of a category, because now I'm going to get into it. All right. Okay, so what's an initial object of a category? So a category, an object I is called initial if and only if for all, A and C, there exists a unique map. I don't know, we can call this, I don't know, I of A from I to A in the category. Okay, so for every object, there's a map like this. So in particular, the empty set is always included as a subset of a set, or the or another way to say it is the zero abelian group is always inside the group. Okay, the opposite is called a terminal object. So an object T is called terminal if and only if for all A and C there exists a unique map and we can call this P of A from A to T. Okay, so this is an initial object and this is a terminal object. Okay, so a good exercise is that a good exercise is to show if initial objects exist, you could say this is for terminal too, then they are unique up to unique isomorphism. Okay, so they're unique up to a unique isomorphism, and that's because we use that this map here is unique. Okay, so now now you're an expert on initial and terminal objects. Okay, so now you have graduated and you know everything there is to know about initial and terminal objects. Don't have corona, don't worry. Okay, so what was I going to say? Okay, so now we were going to talk about recasting products, right? So we have this definition for products, and I want to say something about products. Okay, so recall that so products of two objects A and B, they have a map to A and a map to B. Okay, so let me write this diagram. So I wrote down this diagram before here, and so let me kind of write it in a more suggestive way. Okay. All right, so let me write it in a more suggestive way. And the suggestive way is like this. Okay, so we're going to write A here. And we're going to write B here. All right, and we're going to write C all the way up here. And I'm going to write it like they're down like this. Okay, so I'm going to write a cone. It kind of looks like a cone over here. Okay, so here I'm gonna kind of, maybe if I can kind of highlight this. So there's kind of this thing here. Sorry, so this is the arrows going the wrong way. We have this thing here, and we have this thing here. This clump here, and we have this clump here. Okay, so we have these two clumps. And this clump maps to this clump. Okay, so I'm going to do something that's kind of weird. So this is the universal property of products. Okay, and let me just give you the spoiler here. Is I'm going to make a category, right, where we have objects C and maps to A and B. And I have objects, you know, and I can look at all the possible things that have maps to A and B. Well, it turns out that this product here is the terminal object of this category of cones. Okay? So let me just say that briefly. So the fancy perspective right, is that A cross B is the terminal object. A cross B with, okay, A cross B, let's call it like this, the projection to A and the projection to B, so it has all of that data, is the terminal object in the category of cones over A and B. Okay, so so this is the fancy perspective here. Okay, so that is, we make a category whose objects, so the cones, okay, and the cones in this particular category, I'm going to call this cones D, because this will in general rely on a diagram, right? And this diagram in this particular case is kind of a silly diagram. D is just a diagram where you have A sitting here and you have B sitting here. Okay? There's kind of a fancier perspective of what this diagram is. The diagram is a functor, right, from a category with 2 points and essentially no morphisms to here. So this is, okay, so we'll say more about what diagrams are in a second. But cones D, so what is this thing? So the objects in this particular case for this diagram, so the objects are, well, their objects are C. The objects are collections of, they're like this. They're these C's with maps to A and B. So they're triples. So what is another way of saying this? This is a triple C, F, G, consisting of two things like this. And then morphisms in this category, right? So what are morphisms in this category? So there are, they look like this. Here's C, here's C prime. And so we have a map from, okay, we have A, B here. And we have A, so we have an F and a G like this. But now we have this thing. We have some F prime and we have some G prime. So they are collections of psi's, okay? So these are maps psi. So morphisms are maps psi from C to C prime. So these are morphisms in our category C, such that the diagram to the left commutes. Okay, what does that mean? So that means that psi composed with G prime is equal to G, and F prime composed with psi is equal to F. Okay, so this is what it means to commute. All right, so so now we have a category. This is the category of cones, right? Where this is where we have these two things. So this is the fancy perspective on what a product is, okay? And the definition is so the product. So a product of A and B is the terminal object of the category of cone D whenever it exists. So one of the things that we're interested in is we're interested in knowing when these constructions exist. When do products exist in general? Okay. So again, to recap, there's a universal property, and all these universal properties, actually, for any limit, right? Any limit, they come from. So we had all these universal properties. So it turns out that we can make a new category here. Like we could put cones here, cones over a diagram, right? And the terminal object of that category is what's called a limit, and that's and products are examples of that, right? Coproducts are examples of initial objects in the category of cocones. So it's kind of the opposite, okay? So and those sometimes exist. So that's kind of that's the basic idea for how we're going to talk about limits in general for categories. Is that, well, they're all derived from initial and terminal objects. Terminal objects of the category of cones are limits. Initial objects of the category of cocones. So what is a cocone? A cocone it would be the other way. So how would I do coproducts? Okay. So for coproducts, let's see. Do I have a? Let me stop and get a pen real quick. Okay. So now let's do I got a blue pen. Okay. And now I'm gonna show you how coproducts work. Okay. So here, let me just do the video for coproducts. Okay. So here we had so we had to talk about initial and terminal objects, okay? But now, let's do this. So let's get rid of this. Let's do coproducts. Let's get rid of this here. Let's go A. So that's how we write it for a general category. We just use that symbol for a coproduct. And now, instead of having this, we're going to go the other way. Right? And then these go out. So all the arrows are reversed, and I'll make like a little dot here. Okay? So for coproducts, I'm just going to do the same thing, but I'm going to flip all the arrows. So the arrows go the other way so that they're going to become initial objects. So a cocone is, they come from the diagram down. They come from this diagram, so this diagram just has 2 points up, right? And then cones go down, all right? And then, okay, so then what do we do? So the fancy perspective for, okay, so we have terminal. This becomes initial. This becomes A disjoint union B, or A coproduct B. These are not maps. Now, again, in the previous case, right, before I erase this, an object came here and they had maps down, right? Now there's two maps that go in from the product. Okay, and so this is maybe IA and IB. Okay, so the inclusion of A and the inclusion of B instead of projections. So this comes IA, IB. So this object comes with two maps, IA and IB. And instead of the category of cones, we have the category of co-cones. Okay? So this would be co-cones, right? This would be, so this is co-cones. The diagram, and by the way, in this category, the diagram is exact same. So this diagram is the same. Exactly the same. And I'll say officially what a diagram is in a second. Okay, so now what are the objects? So the objects of the category of co-cones, well, their maps going up. Okay, and they are still triples, but now the maps go up instead of down. And that's what makes them a co-cone, right? So they're, all right. And now, what are morphisms of two objects? Well, they're morphisms like this, except for they go the other way. Okay, so this is the category of co-cones for, so we're going to make a co-limit in it's for the coproducts, okay? And now we need to write this a little bit differently. And so now we have, okay, so we have G, so this is just, yeah, this doesn't work at all this way now, okay? So what we need is we need F psi to be the same thing as F prime, right? So I guess, so we go F psi and then we do F prime. Okay, so these are just totally wrong, right? So the correct condition is that F followed by psi is F prime. And in this one we have G followed by psi is G prime. All right, and then a coproduct of A and B in the category is the initial object of cocone D. Okay, so this is what the coproduct is. So if it exists, okay, and so the hard part, so like it's okay, so now we can write down this thing, and now it's like, okay, I have a general way of talking about products in any category. The hard part of doing all this is actually writing down a construction, right, and then checking that your construction satisfies these axioms, right? That's the point of, that's the difficulty of writing these things down. Okay, so let me stop for a minute, and I'll just kind of do this in general. Okay, so I am now going to, I think, do limits and colimits in a more formal way. So previously, we did all this, right? We talked about these limits, and then I showed you products and coproducts, and I told you they were in categories of cones and cocones. And now I need to do some like legalese, like the fine print for everything here. So let me just start. Okay, so definition. So yeah, let's start with diagrams. All right. This is not the most important video to be watching, by the way. I would read this. So a diagram, right? A diagram. So in a category, C is a functor. Here, D from I to C, period. That's it. That's all a diagram is. And so there's some notation or terminology. We call I the index category. All right. So I is sometimes called the index category. And we talk about, we care about its cardinality a lot, right? So we care about whether it's finite or not finite or whatever. So let me do some examples. So really, so the way that we really think about diagrams is that we think of them as kind of directed graphs. All right. So here is the, we could do A, B goes to C. There's a diagram. Okay. So that's one example. Here's another example, A, B. Okay. So we just don't do anything. Right. Here's another example. Right. So we could have A. Okay. And let's give these F, G. Okay, here's another example. We could have A, B, and then we could have two things like this, F and G. Okay, how is this a functor? Well, really, and then how is this a category? So there's some things to note. So we draw them like this, okay, and they're just like directed graphs in a category, right? But really, we think of this as say in example 1. So with what it really is it's a category with 3 objects, right? So we could call this I don't know. We could call them I1, I2, I3, right? And this category. Okay. So what does it really have? It has this map. It has this map G, F. And then it would, if we had more, it would have the compositions between them. Okay, so there's nothing really to compose here, but it also includes this identity map, and this identity map. Okay, so that's technically part of the category. All right, but when we don't really write all that down, right? Okay, and then so this is okay, and then the diagram here. So we have this functor D, and so really what I called, then we really have D of I3, D of I2, D of I1, right, like this. Okay, and then we really have, I guess we shouldn't call this F and G. Maybe we should call this, I don't know, H12, H32. Okay, and then we have D of H32 and D of H12. Okay, and then this is, okay, so this is what we actually wrote down. We wrote down the image here. Okay, so this is like what the data actually is. And then what we write over here is like an abbreviation of it. Okay, so this is and this is for example A. So or for example 1. Okay, so this is the short way of writing all this stuff. Okay, is there other things that I really need to say about this? I don't think so. Okay, so all right. There is a thing called filtered categories, and I think we'll deal with them when we get to them. Or if they come up, you should read what a filtered category is. And sometimes you need filtered categories for certain colimits. Okay, and colimits again are is the initial object in a category of cocones. All right, so I have this thing on adjoint functors, but let me just say what the category of cones is officially and what the category of cocones is. So so definition. So cones and cocones. Okay, so given a diagram, D, we make the category. I guess we need an index set, huh? We make the category of cocones or of cones. Okay, and so let's say here we'll take D is from I into C. Okay, and we'll call this cone D. Okay, and the objects of this, well, what are they? So they are, okay, so they're an object in the category, right? So we could call it X, okay? And then there are a bunch of morphisms, right? So they are a collection of maps. Let's call them Qi. Okay, for I and I. Okay, so I'm writing the index category. So I called this like I subscript I before, but I'm just going to write the index like that. Okay, so this little I would correspond to a single Roman I here. Okay, where this guy here, X is an object of, so X is an object of the category C, and Qi is a map from X to D of I. Okay, so this is the object, the image of the functor here, where we have D from I to C. Okay, and so then morphisms, right? So morphisms are, so they are maps. So a morphism here. So if I have X to, so if we have Qi, I and I, let's call this F, Y. Let's do X primes. X primes, Qi prime. Maybe I'm going to regret that. Okay, so a morphism here is a single map F from X to X prime, such that. Okay, and I want to say such that the diagram commutes, but I'm talking about diagrams, so I'm going to do a little semantic trick that says that such that we have the following commutation, so that so if I apply F and I then apply Qi prime, so this is equal to Qi for all I and I. Okay, so this is just saying that the diagram commutes like we said before. Okay, so the category of cocones, so this is what we have, right? Okay, so the category of, okay, so then the limit, so a limit of a diagram is a terminal object of cone D if it exists. Okay, so this is kind of just the drawings are in the previous video. Maybe this is not so helpful. I mean, you could have written down the definition yourself. So I'm going to say the exercise is, write down the objects and morphisms for the category of cocones. And the next exercise is write down the definition of a colimit. Of a colimit. Okay? That's all I want to say about cones and cocones. And limits and colimits. As far as like the official terminology goes.